Good afternoon, everyone. Hope everyone's doing all right. Today, I'm honored to introduce Helena Moser. She's a team leader in the Water Resources Branch of the Fort Worth District, U.S. Army of Engineers, Corps of Engineers, U.S. Army Corps of Engineers. She's a professional engineer with over 20 years of experience in hydrology and hydraulic engineering. Helena has worked on a wide range of water resource-related studies, including flood risk management, dam and levee safety, reservoir forecasting, water supply, and environmental issues. She is also an experienced modeler, knowledgeable in simulating complex water resource systems using the latest hydrologic and hydraulic and geospatial software programs. Prior to her current position, she has also served as chief of H&H studies in Fort Worth District and as a hydraulic engineer in the Kansas City District. I'll now pass it over to Helena for her presentation.
Thank you, Carlos. And thank you all for having me. It's a great honor to be able to speak with you all today. Jerry, that spoke at lunch, is my boss, and so you guys got a good introduction to this topic from him, and appreciate the chance to come and talk to you today. So this session, I'm going to go a little bit more in depth on these watershed hydrology assessments that we've been working on, which is once again quantifying for a given storm event, how much water can we expect to run off from the watershed, and especially for these 100-year type events. So first, just a little bit about the InFRM team. InFRM stands for Interagency Flood Risk Management, and it's basically a collaboration among federal agencies. It includes the Corps of Engineers, FEMA, the National Weather Service, and the USGS. So the major agencies that are involved in water resources. And we began a pilot program in 2014 where we basically are trying to leverage each other's experience, information, and resources to try and reduce long-term flood risk in the region. So these are some of the efforts that we've been involved in. Jerry touched on a few of these, but this is the InFRM website, www.infrm.us. You can go on there and you'll find out more information about each of these efforts, including the flood decision support toolbox, the estimated flood elevation viewer, and then the watershed assessments is in the lower right there, which we'll be talking about today. So first, some background. We are doing this under to support the National Flood Insurance Program for these studies, which is administered by FEMA. And so originally, this program was created in the 1960s to help guide the development away from flood hazard areas. And the US government at that time chose the 1% annual chance, otherwise known as the 100-year flood, as the basis for the NFIP. And so the 100-year flow is basically chosen as a balance between, we don't want to be overly stringent in our regulation, but we want to protect the public. And so it's somewhat of a compromise as a standard. But the problem with hydrology is that it is really the single largest source of uncertainty in our flood risk information. You know, we have a little bit of uncertainty in our hydraulic models. We may not know exactly how much roughness there is in a channel or a floodplain, but there's a lot of uncertainty in hydrology. There's also many commonly used and accepted methods for calculating the 100-year flow, and every method you try will give you a different answer. And in Texas, we've seen that this variation between methods can yield up to 20 feet in the depth of a 100-year floodplain. And that's specifically in the hill country where you have a lot of variation in depth anyway. But even in this area, we've seen answers 7 or 8 feet different in the DFW area based on what method you're using to calculate the 100-year flow. So the purposes of the watershed assessments that we've been working on are really to try and produce the best possible estimate of the 100-year or 1% annual chance and other frequency flows across the basin. So we try to employ a thorough approach to hydrology. And what I mean by that is we use a range of several different hydrologic methods and then compare their results to one another as well as to previously published studies in the basin. And this helps us tell the story of how that 100-year flow has changed over time. And it also helps us formulate final recommendations based on not just one answer, but on multiple lines of evidence. So these results that we do from these studies are used by FEMA and others to suggest areas of, here are some areas where we may need to update the floodplain mapping. So this is showing kind of the basins that have been selected and working on so far. So in this map, the green are already completed basins. As Jerry mentioned, the Trinity River, which includes this whole area, was just published last summer. And most recently, the Neches River just came out within the last month or so. But these basins are selected based on where we already have some sufficiently detailed modeling products available as a starting point, and then where those converge with where FEMA has future floodplain mapping activities scheduled. So right now, this is a pilot program, so it's limited to FEMA Region 6, which includes Texas and the other states you see here, but it may be expanded to other areas in the country in the future. So some of the major tasks that are included in these watershed assessments include all the things you see here, and we're going to go into each one of these in a little bit more depth in the remainder of this presentation, but it includes statistical analysis, period of record simulation, reservoir analysis, rainfall runoff modeling, and then comparing those results to one another and investigating reasons for why they're different. And then we also publish a final report, and we go through a peer review process. So first, statistical analysis of the gauge records. So I don't know if there's any hydrologists here, but anybody that's worked around this field for very long, you probably are familiar with Bulletin 17B or 17C. This is a traditional, standard practice of how to calculate the 100-year flood where you have a gauge record. So if you're not so familiar, what we're seeing here on the left-hand graph, that's basically a graph with the x-axis, the year's record at a gauge, and then y-axis is the highest flow that has occurred in a given year at that gauge. And so you take the highest flow from each year and you run it through a statistical procedure, and that helps you come up with the frequency curve that you see on the right-hand side. And that's where you have probability on the x-axis, and once again, annual peak discharge on the y-axis. And so you run this analysis, pretty straightforward and simple. You get your estimate of the 100-year. And that's represented by that red curve. And there is some uncertainty bounds that the analysis will give you around that. But our experiences, most people don't pay much attention to those uncertainty bounds. They're like, I have the answer. That's all I need. Let's go forward and move on. But what we did is we started taking this gauge data and we just started plotting it in a different way for these watershed assessments. So this is that same data with the years of record on the gauge, of gauge record on the x-axis, and that's those points, once again, are the highest flow for that year. And then we started calculating what is the 100-year estimate based on those statistics up to that point in time. So that is what you see in that solid blue line. So you can see, based on the gauge record we had in 1960, we were calculating a 100-year flow of close to 200,000. Then some more decades go by. By the time you get to about 1990, 97, that estimate has been cut in half down to 100,000. And then we got some more floods recently, and that estimate is back up to about 150. And so this type of plot helps us understand better of how those estimates change over time just based on your gauge record. And we're showing this example. This is the Blanco River near Wimberley. Jerry alluded to that horrible flood that happened in Wimberley in 2015. Well, the flood maps for FEMA at this location were actually published in 1997. What you see on that graph is at the low point in the record. So all the flood maps that community had were based on the lowest possible estimate at that location. So this helps us be aware as we're looking at a gauge and analysis Are we at a relative high point in the record? Are we at a relative low point, or are we somewhere in the middle? So this type of analysis, if anyone uses HEC software, it's actually been added as a new option in HEC-SSP, which is their statistical software package. And so this helps, once again, when you're communicating with stakeholders or a community, it helps communicate better than just that confidence band of what is the uncertainty in these estimates and how have they changed over time. It also demonstrates that even when you have 100 years worth of record, that 100-year flow estimate is still a moving target. This graph on the right is from the Neches River near Rocklin, Texas, which has 114 years of record. That's a really long record for Texas. We don't get many gauges with more than 100 years. But even then, that estimate, which is the purple line, is still moving. And some of our statisticians at HEC, the Hydrologic Engineering Center, have shown in their studies that statistical estimates don't stabilize for flood hydrology until you have a length of record that is 3 to 4 times the return period you're trying to estimate. So that means for the 100-year, you'd have to have 300 to 400 years worth of record for it to be stable. And obviously, we don't have anywhere near that in this country. But if you're trying to estimate like a 10-year flood and you have 30 to 40 years worth of record, you're probably in pretty good shape. And once again, this is just another way to help communicate that uncertainty and the effects of changing climate that goes through wet cycles and dry cycles. And these are just some more examples, just kind of give you an idea. This isn't an isolated instance, but we've seen it all across Texas in different watersheds, different gauges. These are all gauges that have 50 to 100 years worth of record, which is considered a long record gauge in Texas. And those 100 and 500-year estimates are still bouncing all over the place in a lot of these locations. So next, another type of analysis we do is period of record simulations in RiverWare. And this is similar to the statistical analysis, but the RiverWare program is a program that allows us to simulate the reservoirs or the dams in a basin as if they had been in operation in their current state for the entire period of record. So in a way, it's a way to extend those records back in time. And so what you see here on the top graph, this is an example from Sam Rayburn Lake, which is the Corps of Engineers dam in East Texas. And so we have the observed pool record, which is about from 1960 something to the present, and then we have a simulated pool back to the late 1920s. And so that allows us to extend the record and understand over that last 90 years or so, how would the dam have behaved? What would the pool elevations have been? What would the outflows have been and the inflows to that dam? And so we use this analysis. One example is on the bottom there from the Neches River, which is at the saltwater barrier down near Beaumont, Texas. And the RiverWare analysis allowed us to effectively extend the period of record for that location from just 17 years of observed data to 90 years using the full RiverWare analysis. Another analysis that we use is doing a more detailed analysis of some of the reservoirs in these large basins that we're studying. And so for this type of analysis, we use a program from the Corps of Engineers Risk Management Center called RMC-RFA. And basically, it allows us to do a little bit of stochastic Monte Carlo simulations based on the data we have from the reservoirs. So you can see on the graph here, we'll have a range of starting pool elevations that we've observed at the reservoir. We'll have a range of different inflow events, inflow volumes and hydrographs. And then we can run it through this program and perform 10,000 simulations. So extending the data rather than just what we've observed, all the different possibilities of what different combinations of inflows and starting elevations and what effect that would have on the dam. So this gives us a better estimate of those rare frequencies of the reservoirs, and especially for things like major dams like Lake Louisville, Joe Pool, some of the major core dams here in the Metroplex. You know, as far as dam safety is concerned, you know, the dam safety community is really concerned with those very rare events, even up to the probable maximum flood. So they use this in the dam safety side of the house also to get a better understanding of the frequency of those very, very large events, like the 40 inches of rain that Jerry had some examples of in the last talk. And then finally, the last major piece of analysis that we do is in rainfall runoff modeling. And for that, we use HEC-HMS, which is another free software available from the Hydrologic Engineering Center of the Corps of Engineers. And so typically for these analyses, we start with an existing model. Corps has existing models available for a lot of these large watersheds in which we have reservoirs in operation. And so we'll use that as a starting point, and then we'll add detail as needed for these studies on the watershed hydrology assessment. So we may increase the level of detail near populated areas or update the terrain based on new LIDAR, and then update the model initial parameters based on that. For these studies, we also try and spend a lot of time with model calibration. And model calibration is basically where we can compare our model results to the observed results at the gauge in terms of flow for a recent storm event, and fine tune those model parameters so that we can be sure that our model is accurately representing the response of the watershed, especially to larger flood events similar to the 100-year, which is what we're most interested in for these studies. So we go through this process, we select several recent large storm events from 1990s to present, which is the time period that we have gridded radar rainfall data available from the National Weather Service. And then we'll adjust those model parameters to get better result. And that's what you see on the left there is blue is the model result versus black is the observed stream flow. And we'll adjust those parameters to try and get the best match possible that we can. When we perform these calibrations, we'll also use some performance ratings just to give an objective means to quantify how good or bad a calibration is. And so these are some of the statistics that automatically the HMS model will spit out for you. And we'll use those to grade it from very good, good, satisfactory, unsatisfactory on the quality of the calibration. So here's just a couple examples. This is the first one, which is for the Pedernales River near Fredericksburg. This is in the hill country region, so very steep, very fast watershed response. You see the river there peaks within just a few hours and then comes down very quickly also. And so this was for the August 2007 storm event that occurred there, which was the largest flood event that happened at that location in at least 25 years. And so this was rated as very good. And then this is another type of flood event. This is on the Colorado River at Columbus, which is downstream of Austin. And so this is from Hurricane Harvey, actually. But you can see here the watershed response in that graph of the black is once again the observed stream flow, and the blue is the model results. In this example, you have a very different watershed response. It's slow to rise and slow to come back down. It takes days for the river to peak at this location because you have such a large area draining into the Colorado River. And so at this location, Hurricane Harvey was the largest flood event that had been seen there since the 1930s, which was another very wet and stormy time period for the Colorado Basin. So all in all, for these watershed assessments, we typically perform calibration on between the 3 to 7 largest flood events that have occurred at each gauge, depending on what data and what events are available. And depending on the watershed, we can have anywhere from 30 to over 100 gauge locations. This is showing the lower Colorado area that we're studying right now and is in progress. And so we have well over 100 gauges spread out throughout the Colorado basin, which includes the whole Austin metropolitan area too. So total, by the time you add it all up, we're performing anywhere from 100 to 400 plus model calibrations per, first adding up each storm at each location. And typically somewhere between 75 to 85% of the calibrations for these studies are rated as good or very good. The ones that aren't, a lot of times there's some problem with the input data. Maybe the rainfall data for a certain event might not be totally accurate. There might be some inaccuracies, or sometimes there's uncertainty in the rating curve at a gauge. And so we'll try and look at, for the ones that don't work out so good, what are some possible reasons for that. So after completing the calibration process for these watershed models, we will then run frequency storms in the models, which this is showing that traditional method of calculating frequency storms. We apply those NOAA Atlas 14 point rainfall depths in the model, and we'll vary it by subbasin. On the left there, that map is showing a map of the Neches River Basin, which is about 10,000 square miles, just in East Texas. And so you can see from the north end of the basin to the south end, that 100-year rainfall varies from about 12 inches at the northern end all the way down to 20-something inches at the southern end near Beaumont. So there's quite a bit of variation in that 100-year rainfall estimate across the basin. But the traditional method is, you can put in all those different rainfall depths as variable for each subbasin. But then using what we call the uniform rainfall method, all those rainfall depths are reduced uniformly across the watershed based on the area you're trying to analyze. So this method is primarily most appropriate for smaller drainage areas. And by that, I mean up to approximately 1,000 square miles. But some of the limitations of that method is that they're based on these TP40 depth area reduction factors. And so that graph on the right is figure 15 from TP40, which was published in 1961. And there really aren't a lot of good, solid depth area reduction studies that have been published since then. So these curves that are from TP40 are what's already programmed into HMS. If you try and do a depth area analysis, it will use these curves. But the problem is that TP40 only studied data out to 400 square miles. And that's just because they were limited on the amount of data that they had at that time. Whereas the basins that we're studying are anywhere from 4,000 to 40,000 square miles. So to better account for how the storms move and are reduced for these very large basins and drainage areas, we started applying elliptical frequency design storms to these watersheds. And that's what this slide is showing, a couple of examples. Once again, we are still using that NOAA Atlas 14 rainfall depth at the center of the storm, and then that depth is reduced as you move outward from the storm. And the depth area reduction curves that we're using here, especially for those areas that are larger than 400 square miles, are coming from regional observed storms that we've calculated. So we move these storms around, and we actually find the optimal location to put the storm above each location of interest on the watershed. So that's why you see these two different storms. These are both for the Neches watershed. One is above the 100-year storm above Neches River near Neches, Texas. And then as we move further down on the Neches River, that storm will move to an optimal location above the gauge near Rockland. So this method of applying rainfall to a rainfall runoff model and estimating the 100-year and other frequency storms is more appropriate for the larger drainage areas of 400 to above 1,000 square miles. And then this is just showing a little bit more about how we calculate those depth area reduction curves. This is some examples of just using observed storms, once again, in HEC MetView, which is a free program for processing rainfall data. And so we'll take the hourly rainfall grids from the National Weather Service for a storm and calculate, based on the highest point rainfall for that storm, and then as you move out, how does that depth, that point area reduce as you move out from the center of the storm. And so this allows us to generate depth area reduction curves out to 10,000 square miles based on these storms, these recent storms that we've seen in the region. And then once we do that, we have some custom scripts that we've built to actually build the elliptical storm itself. And the diagram on the left is showing kind of the general process of taking the NOAA Atlas 14 grids and extracting the data and then applying that depth area reduction raster. And then when you merge those two together, you get a reduced NOAA Atlas 14 rainfall for a given duration that you're interested in. And we're actually working with HEC now to eventually get some of these scripts integrated into the HMS software itself in a future software release, most likely. So some of the lessons learned that we've learned from modeling and studying these elliptical type design storms. There's some factors in the elliptical storm input that it's very sensitive to, and there's factors that it's not really that sensitive. And so we've done a lot of testing, some sensitivity tests to see what we need to look out for. The first row, obviously, it's sensitive to the NOAA Atlas 14 depths, as it should be. On the bottom, it's also sensitive to the location where you put the storm. But we found that it is very sensitive to that area reduction factor. And so that's where it's important to really look at a lot of those regional storms that have happened to make sure that the area reduction curves that you're applying are appropriate for the watershed that you're looking at. But other things like the ellipse ratio, which is the x-axis, the y-axis of the shape of the storm, even the temporal pattern of the storm, of the rainfall over time, not very sensitive to those, maybe plus or minus 5% in the results. So we have some published depth area reduction curves that have come out of these InFRM studies. And one of the surprising things that we found is that those depth area reduction curves for different regions of Texas really didn't change very much. We have ones that we saw from the Guadalupe River down in the hill country, from the Trinity River in this area, and then the Neches River in East Texas. And they're all surprisingly similar in how that point rainfall is reduced by area. So that's a resource that's available also if you need to apply this type of analysis, that you could just use some of those already published curves. All right, so once we finish all these basic analyses, we take the results and we start plotting them in different ways, comparing them to one another. So these are just a couple of different types of plots that we'll do. The one on the left is your traditional frequency curve plot, where you have discharge on the y-axis and probability on the x-axis once again. And we'll have lines from all these different types of analyses that we've ran and compare the results to one another, along with some confidence bounds for those analyses. We'll also take one of those change over time plots and then plot the model results on top of that and see how does the model results compare to the gauge record, and is it high, low, or in the middle. So a couple of examples I'd like to talk a little bit more about is where we see some pretty significant differences. How do we resolve that? And we have a few different tools in our tool belt that we can use to do a little bit further analysis and try and add another line of evidence, basically, to say what do we think is the correct answer. So one of those tools that we use is 2D HEC-RAS analysis. So this is an example. It's in the Neches River Basin above Sam Rayburn Dam on the Angelina River. And this is a gauge that has about 1,200 square miles of drainage area. And this just happened to be a location where our elliptical storm results came out significantly higher than the statistical results for this gauge. So we started, wondering, well, why is that? Well, we started looking a little bit more into the gauge data for this location. And we come to find out that the largest flood event that has ever occurred at this location is that 1989 flood. And when we looked into the historic records for that flood, we found that it was produced by about 9 to 11 inches of rainfall over 2 days. And so if you compare that to NOAA Atlas 14, that's about a 25-year rainfall event. So that tells us that even though this gauge has over 60 years of record, it has not experienced anything more intense than a 25-year event. So that's an indication that those statistical results might be skewed a little bit low as a result of that. One of the problems with statistical analysis of gauge records is just that it's very sensitive to sample bias. You can have a gauge that's very unlucky, that has a lot of very large events, and you're going to get a very high estimate. You can have another gauge that's been very lucky and has not experienced anything very deep or very intense in terms of rainfall. So that will skew the results to have a lower 100-year estimate. So, but we wanted to confirm once again, which line of evidence to believe more. So as a result of that, we also did a 2D HEC-RAS analysis, which is the hydraulic model from the Hydrologic Engineering Center. And basically applied a rain on grid analysis using the LiDAR data for the basin. And so the nice thing about the 2D rain on grid analysis is you get to account for more completely the physics of how that water runs off based on a given storm event. And so what this showed us is it helped us capture that difference in the watershed response based on, are you getting a moderate rain versus a very intense rain? And so there you see in that graph the difference in that watershed response from a 2-year rainfall versus a 100-year rainfall. The more intense the rainfall, the watershed, the runoff starts moving more quickly. The runoff response becomes faster and more intense. And so we need to account for that when we're trying to estimate a 100-year flood based on these models. So we used the results from this 2D analysis to help inform the final parameters that were selected in the rainfall runoff model. And then this is another example from here in this area. This is Mary's Creek in Fort Worth, Texas. And once again, we used 2D HEC-RAS model to help us understand how Mary's Creek would respond for a 1 inch per hour rainfall versus a 5 inch per hour rainfall. And this is another watershed that we'll come back to in just a minute that has not seen a very intense rainfall event from the records that we have available. So finally, another tool that we have in our toolbox that Jerry talked a little bit about in the last talk was the swarm shifting investigations. And I'll show how we use these investigations to help us on the watershed assessments. So this is an example, once again, of the Neches River, the saltwater barrier, which is near Beaumont, Texas. And so this is once again one of those change over time plots based on the RiverWare data. And then we overlaid our modeling results as straight lines over that. So the purple is the 100-year and the red is the 500-year. And this particular gauge was significantly impacted by Hurricane Harvey. The Neches River in this area saw between 26 to over 40 inches of rain over 5 days in that event. And the the rating curve, the discharge rating curve for this event was exceeded by over 10 feet. So we were trying to forecast during the event, and the National Weather Service and the USGS really had no idea what was coming downstream because it was so far beyond any other event that had occurred at this location. So what we saw here, and what, as you can see on the graph, are elliptical storm results from the rainfall runoff model are just a little bit lower than the current statistical results. And we just looked at that and said, okay, which is more true? Are the statistics a little high or the model results a little low? So to help us confirm that, we use a storm shifting analysis. So we selected 3 recent nearby storms that had occurred, and we just shifted them, just as the hourly records were and the spatial distribution and all that. We just shifted it to a critical location above the saltwater barrier. And when I say shifting, we generally just shift maybe within 50 miles or so from what the position where it occurred. So the rainfall depth of these shifted storms ranged from a 50-year to a 500-year depth, according to NOAA Atlas 14. And then we ran those shifted storms in the rainfall runoff model with a range of soil loss rates. So from ranging from average conditions to wet conditions, and then recorded the model results at the saltwater barrier. So what this did is that helped bracket the elliptical storm results from the rainfall runoff model for similar frequencies. So if you look on that graph, the light blue dots are the elliptical storm results, and then the 2 red lines that are kind of dotted are the results from those shifted storms. So depending on if you assume average soil conditions to wet soil conditions, it kind of brackets right in the middle those elliptical storm results. So, and both of these, it also plotted the yellow curve on that graph is the RiverWare statistics. So what this showed us is the RiverWare statistics are on the high side right now. They're on the very wettest assumptions compared to the NOAA Atlas 14 and the shifted storm results. And that's likely due to the influence of Hurricane Harvey. Anytime you have a huge event like Hurricane Harvey in your gauge record, it's going to tend to skew your gauge analysis results to the high side. This is another example. This is in Fort Worth once again. It's the Clear Fork Trinity River at Fort Worth. And this is another example where we use storm shifting. So this location is actually just a short distance downstream from that Marys Creek watershed that we spoke about a minute earlier. It's also downstream of Benbrook Lake, which is a Corps of Engineers dam that controls a large portion of the watershed. So this USGS gauge has about 60 some years of record. But what we found here was that when we first compared the results, not only was the rainfall runoff model results well above the statistical, it was actually above the 95% confidence band of the statistical results. So that caught our attention really fast. And that's what you see there on the graph. The blue dots, once again, are the largest flow that has happened in that year at the gauge. And then the blue solid line is the 100-year estimate based on that record up to that point in time. And the red lines are the confidence bounds around that 100-year estimate, just based on the gauge record. So you can see the black line up there is way above that. But once again, we started looking at why is that? And we found in this case, the largest event that has happened in 60 years at this location was May 1990, which when you look back at the rainfall records, only resulted from about 3.8 inches of rain, which is not a very large rain event at all in the grand scheme of things. That's about a 5-year rainfall, according to NOAA Atlas 14. So this would appear to be a gauge, once again, that has been very lucky, that has just never had that large 10-inch rain that we normally design for. So we did the same type of storm shifting analysis for this gauge also. And so the map on the right is showing to the right-hand side, you see the Clear Fork gauge, its location relative to the uncontrolled watershed that is above it. And so Mary's Creek makes up a major portion of that watershed, and then the rest above Benbrook Lake is controlled by the reservoir. So when we looked at this, just that uncontrolled drainage area, we found that the available calibration events that we had only produced about 1 to 2 inches of runoff. So normally we consider those to be relatively small events. So what we did for this analysis is we actually took a June 2000 storm, which had 10 inches of rainfall that fell above Benbrook Lake. And during the actual event, that rain was just absorbed into Lake Benbrook, and it never, it was released very slowly, so you never saw a large flow at the Clear Fork gauge. So we just took that event and we just moved it 10 miles north, or 15 miles north to Mary's Creek as a what if. What would have happened if that 10-inch rain happened 15 miles north instead of where it did? And what we found from this is that the model results from that June 2000 shifted storm were very similar to the rainfall runoff results from the 100-year storm that we had run earlier. And you'll see that on the graph on the right there. You see that black dot is the June 2000 storm on the right, which is just above the calibrated HMS model results for the 100-year. We also, as a sensitivity test to the gauge analysis, the 17C gauge analysis, we added that shifted storm back into the Bulletin 17C statistical analysis just to see what would happen. And just adding those shifted storms increased the 100-year statistical estimate by 100%. It doubled from 25,000 CFS to 50,000 CFS. And even that 95% confidence bound, the upper one, moved up by 80%, increased from 50 to 90,000 CFS. So this just confirmed just how sensitive those gauge statistics are to 1 or 2 events that they have occurred slightly differently at slightly different locations could have produced very different results at this location. So once again, that 17C statistics are very sensitive to sample bias. It assumes that you've had a representative sample of flood events that have occurred in that watershed, which you could have actually been lucky or unlucky, depending on the type of events that happened there. All right, so that's most of the heavy technical stuff. After we get through all these different types of analyses, we put out a draft report and technical appendices, summarize all this, and we send it out for peer review. And so we try and include different experts in water resources and hydrology from across the state to participate in the peer review process. So we'll have subject matter experts from the different federal agencies peer review it. We'll have regional stakeholders, which may include river authorities, water and drainage districts, councils of government, cities and counties, different stakeholders in that basin, as well as different state agencies, including the Water Development Board, TxDOT, and the General Land Office. We also participate with what we call the InFRM Academic Council, which is just a grouping of professors from different universities across Texas that participate in this peer review process with us. So the peer review comments that we receive and the responses are published with the report in an appendix. And then the final reports from these studies are published on this InFRM website. And these reports and appendices are available for public download. We also make the models themselves available at no charge. Just they're provided upon request. So you just have to reach out to us. And these results from these studies are recommended by this group of federal agencies as best available flood risk information for use in any future studies. So finally, just some results and applications from these studies. This is just a comparison of the 100-year flow results from the InFRM studies versus previously published FEMA flood insurance study flows. And what we saw is that there are significant differences from the effective flood insurance studies in many areas. But those differences vary. There's some where much higher, somewhere it's much lower, somewhere it's about right. And that's where these bar graphs are showing just different selected locations, where the green is the InFRM watershed estimate, and then the blue bars are the currently effective flow, 100-year flow for that location. But one of the things, that we see over and over again is that a lot of times the flows, the hydrology behind the current FEMA maps for a lot of these large rivers has not been updated in 30 to 40 plus years. So even when FEMA is putting out new mapping updates and modernizing their maps, a lot of times they never go back and update the hydrology. They'll like update the LIDAR, they'll update a new hydraulic model, but those flows still go back 40 years and are just carried forward in many cases. So some of the reasons that we see for the differences, and especially where we see an increase in the 100-year flow, a lot of times it's due to rainfall depths. As Jerry alluded to, those NOAA Atlas 14 had significant increases down near the Gulf of Mexico, as well as in southern Texas and near the hill country. It can be due to urbanization in an area like this, especially that's undergoing rapid development. And then also it can be due to that gauge sample bias from 17C. There's a lot of FEMA studies that are just based on the Bulletin 17B or C analysis that were done at that point in time. And so if that hasn't been updated in 40 years, you can have a lot that's happened since then that would change that estimate. Another comparison we've looked at is to the base level engineering data, and that's those approximate HEC-RAS models, and the HEC-RAS models that are available from FEMA and the InFRM website. And those are good models. They just use approximate methods for the hydrology behind them. And so we compared those, and there are areas where the flows came out pretty similar, and there's others where the difference was over 80%. And that's what that bottom left graph is showing, just differences at different locations in the Neches Basin. But one of the big things to be aware of if you're using that base level engineering data is that it does not account for reservoirs. And so we know they say in the notes it doesn't account for structures. And it's, most of the time we think of bridges, culverts, things like that. It's one thing not to account for culvert. It's another thing not to account for Benbrook Lake or Lake Louisville. So what that data plots is it'll plot the floodplain as if those reservoirs do not exist. So that plot on the lower right is showing a comparison to the BLE data at Sam Rayburn Reservoir, which is a Corps of Engineers reservoir in East Texas. And it's actually plotting the 100-year lake elevation at below normal pool for that lake. So it's way low, whereas the analyses that we did had it way up near the flood pool and near the emergency spillway crest. So what this has the effect of is those BLE elevations are much too low upstream of the dam, and a lot of times they're too high downstream of the dam because they don't account for any of the flood risk management effects of the reservoir downstream. Some other applications of how these watershed assessments are being used in Texas. FEMA is using them to update their hydrology and any of the new mapping updates that they're doing across the region. So some examples, this has already been applied for the middle Guadalupe River, and that map on the right is showing you the new results that incorporate the InFRM hydrology into the Guadalupe River modeling, and that's near Gonzales, Texas. And then they've also been implemented in the East Fork Trinity River and Trinity River near Rosser in this area. And they continue to add on as FEMA has budget and planning for different mapping updates. We also use them to help communities add detail for local floodplain updates and on smaller streams in some of these basins. So this is One example is for the city of San Marcos. We studied the Guadalupe River Basin, but could only go to a certain level of detail. And so the city of San Marcos asked us to help just update their floodplain and their hydrology for some of the smaller streams in the basin. So we were able to apply some of the same methods from the hydrology assessments to come up with consistent estimates for some of those smaller tributaries. We're also looking at updating some of that BLE data to take more detailed hydrology information and put it into those hydraulic models so we have a better estimate available on the BLE data. And we're working with the Texas Water Development Board, and they're actually taking wherever we have a watershed assessment that's published and where they're producing the new 2D BLE data, they're dictating to their contractors, hey, you guys need to check the flows that you're coming up with against these other hydrology results and make sure that they're in alignment with one another. These methods that we're talking about today are also being applied in the Texas General Land Office's river basin flood studies. Some of you may have heard of those. They're being done for a large swath of Texas, especially along the coast, where they're doing a lot of planning and flood risk management studies in those areas. And those studies are using a lot of the same methods that we talked about today. And then once again, these results and models are available upon request for other future studies. And that's all I had. So be happy to take any questions. My contact information is on the screen. If you'd like to follow up afterwards with any additional questions. Yes.
How often do you think those watershed hydrology assessments will be updated? And then I know you said the new BLE data might incorporate them. Do you think they would go back and update since where they've already done BLE to incorporate your assessment?
There is a plan to do that. As far as when to update the overall watershed hydrology assessments, I think it's going to depend. It's going to vary by basin because not every basin is experiencing as rapid development as, say, Dallas-Fort Worth is. But we are also looking at incorporating as an addendum to these studies another estimate of future hydrology. So looking at future land use, and so we can have at least an existing and a future estimate for future development. Yeah, and then the BLE data, that goes in cycles depending on the who's funding it. So far it's been FEMA and the Texas Water Development Board that have funded those studies. So they're on like a 5 to 10 year cycle. Right now, they're just trying to get all of Texas modeled and, get something out. But once they get, the whole state covered, then they'll go back to the beginning and say, okay, what needs to be updated and start bringing in some of those updates to those models. But I would say probably a 5 to 10 year cycle for that.
Has it been looked at how these flows compare to ultimate flows that are in some city models?
So usually it depends on the funding source or the customer, right? So these studies that we're doing for FEMA doesn't necessarily look at future or ultimate conditions. But if we're partnering with a city or county, somebody that does, then yeah, it's fairly simple to take. There's only so many parameters that have to be updated to take that modeling and then update it for ultimate conditions. Right now for the Trinity, we're working with the North Central Texas Council of Governments, and so they have an estimate of land use for like 2055. And we'll use that. It's not ultimate, but it's at least a point in the future that we can reference as this is the existing flows and this is what 2055 might look like. Yes.
Just out of curiosity, I have a project in Pedernales back in the 90s, and at that time, the emergency feel like a pink light press for the first time. The Deal Lake emergency spillway also pressed. Do you have any clue what size storm those things were?
Is that 2002 or 98? Okay, yeah. October 98 on the Guadalupe River was a huge event. So it kind of depends on where exactly, what point you're looking at on the Guadalupe River. Yeah, so I think those were at least a 100-year event, maybe more. And then by the time you got down further downstream to like Victoria, it's more like a 200 to a 500-year event because it got, I mean, we got anywhere between 20 to 35 inches of rain in that October 98 storm event at different locations in that area. So it was a monster storm event. Right. Yeah, and we used that storm as one of our calibration events. So we used that to try and make sure our model was matching what happened in that storm event. Right. Yeah, it's incredible. Any other questions? All right, thank you.
Awesome. You did awesome. No, you did great.